Hi, I'm Song from RT McBain Department of Chemical Engineering at Texas A&M University. Today's presentation topic is the integration of offset-free control framework with Koopman-Lyapunov-based model predictive control. The presentation consists of following contents. First, the preliminary part. The linear predictors for nonlinear dynamical system allows the utilization of established control methodologies for linear system and computationally tractable online controller design. The key step in obtaining accurate linear predictors is lifting of the state space to a higher dimensional space where the evolution of the lifted state is approximately linear. This framework can be rigorously justified by Koopman operator theory. For uncontrolled dynamical systems, Koopman suggested an operator-theoretic perspective that transforms a nonlinear system into a higher dimensional space of observables. In this space, evolution of observables is governed by an infinite-dimensional linear Koopman operator. While the nonlinear operator and the Koopman operator act on different spaces, they encapsulate the same dynamics. The particular interest is not the Koopman operator itself, but a proper linear predictor. Several algorithms are developed to approximate infinite measure Koopman operator. The extended dynamic mode decomposition is one of the most commonly used algorithms. In EDMD, controlled system dynamics is considered by introducing a vector of observables consisting of function of x and u, and the Koopman operator associated to the evolution of this observer can be described as follows. Then an approximation of input variable approximation of Koopman operator is derived by solving the optimization problem with time series data set. But since the dynamics of input variable is not needed, the optimization problem can be reduced as follows. And then the analytical solution from the problem lifted state space can be derived. And there are several Koopman-based MPC that apply the lifted state space model from EDMD have been developed, but let me introduce the Lyapunov-based MPC first. The MPC applies Lyapunov constraint to the optimal control problem based on an explicit stabilization control law and Lyapunov function. The first Lyapunov constraint ensures that the closed-loop system stays within the stability region. And the second constraint guarantees that the Lyapunov function value at the next time step is smaller than or equal to the value from the stabilization control law. And by this, the NMPC scheme can ensure the feasibility and closed-loop stability of the control system. However, there is a limitation that due to the nonlinear dynamics and nonlinear constraints, the optimal control problem becomes a non-convex problem. To handle this limitation, the Koopman-Lyapunov-based MPC is developed to integrate EDMD and LMPC. In this scheme, the nonlinear dynamics is approximated with a linear predictor via EDMD, and nonlinear functions in Lyapunov constraints are observed into observable function library. And by this, the Lyapunov function value can be simply derived from the lifted states value. And by applying this formulation to the optimal control problem, the nonlinear dynamics and the nonlinear Lyapunov constraint can be reformulated as the linear dynamics and the linear constraints. By this, the optimal control problem of KMPC is formulated as a convex quadratic problem. And consequently, KMPC scheme allows to avoid solving a difficult non-convex optimization problem. This section presents the proposed offset-free KMPC framework. Then KMPC has a limitation since the data-driven EDMD derives a finite dimensional approximation of infinite dimensional Koopman operator. Thus, the inherent plant model mismatch occurs, and this can degrade the closed-loop performance of MPC system. Therefore, the handling of this plant model mismatch is essential in KMPC scheme. Hence, the integration of offset-free control framework with KMPC is proposed in this work. The disturbance estimator approach is one of the most commonly used offset control scheme. Therefore, we apply the disturbance estimator approach to ED&D model. And in this scheme, the disturbance dynamics and disturbance influence on lifted state and output are augmented to the lifted state space model obtained by EDMD. And here, the disturbance variable represents the sources that cause prediction error, including plant model mismatch. And then the disturbance estimator is designed based on the disturbance augmented model. And the estimator gain, LG and LD, are set to make the estimator stable. Then the target lift state and input are derived from the set point value and the estimated disturbance value by utilizing the set point tracking condition equations. And then the proper target values considering the influence of disturbance are derived by solving this equation. Of course, the solution would exist with proper reference signal value, but it may not be unique. Therefore, the target pair is obtained from the target problem considering the desired values and the process constraints. Then, given the lifted state and input targets from the target problem, a final horizon optimal control problem can be brought into a lifted state regulation problem with Lyapunov constraints. In this formulation, the equilibrium point of Lyapunov function and stabilized control law are determined by the current target Z bar. And since the target of the optimum control problem, Z bar, is continuously updated over time by the target problem as the disturbance estimate is updated from the estimator, the Lyapunov function and the stabilized control law also need to be updated over time. The updated Lyapunov function can be reformulated as a affine function of lifted state by applying each term reconstructed by the lifted state. And the updated Lyapunov constraints can be reformulated as linear constraints by applying the affine form of Lyapunov function. The stabilized control law is formulated based on the state feedback under disturbance, and M bar and KD are derived from the set point tracking condition at steady state. This flow diagram illustrates the offset frequency system. And the disturbance estimator estimates the lifted state and disturbance from the planet measurement, and then the target lifted state and target input are derived from the target problem, which disturbance estimate and the reference signal. And then the optimal input for plants is derived by solving the optimal control problem with Lyapunov constraints, which is updated as the previously introduced procedure. This section presents a numerical example. The CSR system was utilized as the virtual plant for the numerical example. In this system, the first order reaction was considered, and the parameters in this table are used in CSR simulation. In this simulation, the outlet temperature and outlet concentration are set as the controlled variables, and jacket temperature and outlet flow rate are set as the manipulated variable. Then a lifted state space model was identified through EDMD. And this EDMD, this observer library was used, and the time series data set generated from the operation of the virtual CSR are used. And then the series of step input in jacket temperature and pulse input in outlet flow rate are applied for validation of the derived EDMD model. This figure shows the resultant output trajectories. As you can see, while the lifted state space model seems to properly predict the behavior of the virtual CSR for the most part, the prediction error still exists at some part due to the inherent plant model mismatch. The closed-loop simulation is performed based on the derived lifted state space model, and this figure shows the resultant output trajectories. As we can see, the control variable C and T trajectories induced by the nominal KMPC scheme show the considerable offset from the set point values due to the plant model mismatch, while the trajectories induced by the proposed offset frequency KLMPC scheme showing the general offset steady state of tracking. In this figure shows the estimated disturbance values from offset KMPC. As you can see, when the set point changes, it takes some time to derive proper disturbance values. So the trajectories of C and T show a direct deviation from the set point values near set point change. And nonetheless, the disturbance values derived from the stable estimator converts to proper values. So that's why the proposed offset-free KMPC scheme can achieve the zero offset tracking property. Conclusion: we propose the offset-free KMPC framework to address plant-model mismatch in the KMPC scheme, which is inherent to upload in data-driven AD&D caused by a finite dimensional approximation to the infinite dimensional coupon operator. In the proposed framework, unlike the nominal KMPC scheme, the equilibrium point of the optimal control program is continuously updated with disturbance estimate. Therefore, the formulations for updating the Epsilon function and stabilizing control law are also developed. Additionally, a mathematical analysis for the general steady state offset condition of the proposed framework is performed. Therefore, the developed offset-free KMPC framework is expected to provide a variable direction for addressing the plant model mismatch that is inherent in Kuppner operator-based predictive control methods. Acknowledgements. Thank you for listening.